To appreciate beauty is to reach up to the pinnacle of human experience. Whenever I appreciate beauty, however fleeting the moments, all else dissolves. Beauty is everywhere. We recognize natural beauty in radiant flowers and dazzling sunsets. We revel in composed beauty, like soaring music and magnificent art. We know what it means to call a woman beautiful. But what does it mean to call the universe beautiful? What is it about the construction of the cosmos that evokes visions of beauty? Great scientists see great beauty. I'd like to see it too. I'm Robert Lawrence Kuhn, and closer to truth is my journey. Peter Atkins is a distinguished chemist and a literate expositor of science. When he describes how the world works, I am swept up, as I am with a Mahler symphony. I seek beauty in science, which is why I start with Peter. He's professor at Oxford, where we meet. Peter, I was very moved by your book in which you discuss symmetry and beauty and showing the importance of that in science.
Yeah.
Why is symmetry so important?
Well, everyone's got a gut feeling that it's important. If you dig right down into the substructure of the world, then you find what is effectively beauty, but we call it symmetry. That you find that you can talk about the fundamental particles in terms of their symmetries. As you work up through the systems of the world, as you move away from the fundamental particles and you come to the properties of matter, you then find that you can discuss, say, chemistry in terms of symmetry. And then you can sort of take it even further, and you can start to talk about the symmetry of biological entities that emerge from all this underlying structure, and find that symmetry lies there as well. I suppose at its crudest, nature decided that it was more economical to think of one half and let the other half just tag along. So, I suppose a synonym for symmetry is simplicity. And if you go for the simplest route, then you really go for the symmetrical route, that there's less to plan if you just think of one module that can be replicated a number of times. But the emotion of seeing this gorgeous symmetry, it really is a visceral feeling of beauty. And the amazing thing about symmetry, of course, is that it's not just a woolly concept of, that's nice. It really is something that can be rendered quantitative and expressed numerically. And once you start attaching numbers to things, then you have a real grip on their properties. If you think that you have got a very symmetrical structure in your equation, it just feels right. Your heart warms to the equation. But of course, that's not quite true if you look at things in a more global way, because we know that the universe is apparently not completely symmetrical. There are broken symmetries, and it's one of the pleasures of the world. And I suppose if you were to take it to extreme, the very fact of existence is that symmetries are not exact, they're slightly broken.
Well, that's great art.
It's great art, absolutely.
Great art, if it was perfectly symmetrical, would be boring and childish.
And it's that nuanced, broken symmetry that actually gives the richness of the material world.
Symmetries are essential. They work their magic all the way down. From organisms, to cells, to molecules, to atoms, to subatomic particles. But symmetries cannot be perfect. They must be broken, or else interesting things wouldn't exist. Is symmetry beauty? Is beauty a human perception or a basic reality? What could be more fundamental? I ask a mathematician. Roger Penrose, also at Oxford, is one of the world's most distinguished mathematicians. Roger has visualized things that no one else ever has. How does he see beauty?
Well, beauty is certainly a very essential part of understanding and doing mathematics. It's one of the reasons, one of the key reasons one does mathematics, is the beauty in the subject. There's also a fact, it seems to be a fact, that the laws that very closely govern the activity of the physical world have their own kind of beauty. I think there's something in saying that what's beautiful in mathematics tends to be when things turn out to be simpler than you expect. I mean, you could say, well, you're pleased because you sort of understand it when you didn't before, and this gives you this feeling of beauty. Or is there something deeper in which the beauty is somehow in it? There's a certain amount of beauty in things being not quite symmetrical, you see, but they have. But in the deviation from the symmetry, you see some other structure and some other pattern, which somehow can have quite a lot of elegance to it.
That's an interesting new word, elegance.
Well, elegance is often used by mathematicians, I think.
Yes. How do you either contrast or relate elegance and beauty?
There is a kind of refinement about it, I suppose, that one sees in mathematics. I mean, it's not something that stands, sort of shouts at you. You have to understand it before you see.
What you said was interesting, that beauty is simplicity, but sometimes it's not perfectly symmetrical, it's almost symmetrical, and that deviation from the symmetric enables other things to happen.
Yes, and the asymmetry probably has some character. It's not just asymmetrical. You see, there is something, you follow that route and you see there's something deeper going on, which explains why it's not completely symmetrical in the most obvious sense. I mean, what it is that is the essence of beauty or elegance or so on is very hard to get hold of. And it's not just symmetry. I mean, symmetry is certainly something which can be beautiful. You see this in sort of platonic solids, and you see, it's nice, you look at this and it's really the same, whichever way you look at it. And is that beauty just because, okay, I only have to look at a small part of it, and by knowing the symmetry I can extend that to the whole thing? Or is there something else there which is really why it's beautiful? I think it's unexpected relationships and things like that, which often needn't be symmetry, but you suddenly see things line up in ways that you hadn't thought of before. And that can have quite an aesthetic appeal. It also goes along with depth. I mean, there are certain mathematical things which are deep in the sense that there's a lot more to it, and it's somehow doing a lot for you. You had no idea, no reason to believe in the first place. It's not put there by us. I suppose that's the difference between the beauty in mathematics and in art, where, okay, in art you see, despite, Michelangelo saying his statue was there in the rock all the time and he was only revealing it, you see, somehow he's doing it, you see. Sure. Whereas in mathematics, you're revealing it. It's there all the time. You're doing your best to kind of bring that beauty out. And, okay, there may be subtle, clever things you can do, which in little tricks, and they may have beauty of their own, but the real beauty is there in the mathematics. Or I might use the term God-given, you see. Somehow we're revealing it rather than creating it.
The real beauty, Roger says, is in the depth of the mathematics. Being revealed, not being invented, always there. Always where? Beyond the human mind? Existing forever? What could that mean? Are science and art similar? There's a gathering in Iceland where physicists gaze over the horizon. What do they Iceland is ideal. Amidst its majestic splendor, I meet Stephon Alexander, a physicist and a musician. He studies the origins of space and time, and he plays the saxophone. Born in Trinidad, raised in the Bronx, Stephon is professor at Haverford.
Stephon, how do you see beauty in physics?
I am a big music lover, and I've played the saxophone, I'm a jazz musician. In a lot of ways, I see physics as musical. Okay, there was a time when I didn't know if physics was a thing for me. So actually, I decided to leave. And right before I was leaving, I had to pack my books, and I noticed somebody else's book, and it was a book on quantum field theory, and it said quantum field theory is the paradigm of all physics, and it basically said all of matter, not only the forces, but matter itself, are all unified under the principle of vibration. That all these things are nothing more than a vibrational pattern, like an orchestra. Wait a minute. So physics is about music. It's about harmonies in orchestra, literally, like waves.
Yeah.
So if I learn quantum field theory, then I can learn some things about music, or I can think about music in terms of quantum field theory. Let this be my little secret. So I actually took a quantum field theory class, and everything changed, and I remained. And it's amazing that that was 14 years ago or something like that.
And so you see the same principles.
See the same principles, or very similar principles between music and quantum field theory.
Yeah, let's talk about some of those principles and try to color those principles with words, as hard as it is. So you mentioned one, harmony.
Well, I mean, if I I play for you, a blues scales, right? Ba-da-da-da-ba-da-ba. Why does the blues scale sound so funky, right? Why does it sound so cool?
Yeah.
It's because of the way those notes are related to one another.
Right.
Or in a sense, the way those vibrations of, say, whether it's the piano or your horn, your guitar, those vibrations have a relationship to one another. And we hear those relationships and we find them pleasing. It affects us.
Right,
We don't know why, but it just does. Quantum field theory is saying that matter is nothing more than a vibrational pattern. And the way different types of matter are interacting with one another, similar to music, are just relationships of these vibrational patterns. And these relationships give you what we observe to be beautiful, or truth, or reality. And there's also dissonance. I mean, there are notes that actually sound displeasing to us.
Right.
So, same thing in physics. If nature was completely following the strict rules of symmetry, nothing interesting would happen.
Yeah.
Somehow the symmetries had to be very interestingly broken. So, same applies in music.
Music and mathematics, art and science. The harmonies seem startling. But why? The creative invention of human intellect, or deeper reflections of an unknown reality? The distinction is stark. Invention or reflection? I am consumed by not knowing which. Happily, Fotini Markopoulou is also in Iceland. A Greek physicist working on the foundations of space and time, she's at the Perimeter Institute in Ontario, Canada.
Usually people translate beauty into mathematics. So if your physics has a lot of mathematics, then it is beautiful. Mathematics is simple, it is elegant, it can tell you a lot of things, it's powerful, and it is a miracle that so much of our world that seems to be imperfect in so many ways translates into beautiful mathematical equations. The question, though, that comes next, in my mind, is this true? Is this what is beautiful?
Yeah.
Recently I was in a meeting with architects. One of the architects made a comment that I thought was really what's going on in what we do. So he compared the academia architects, which are the university professors of architecture, with the real architects that build buildings. And the academia ones make beautiful designs of beautiful buildings. The real ones have constraints. They have a small budget, probably a problematic location, water in the foundations. So the question is, which of the buildings is beautiful? And you could say that, of course, the one that you can make out of your free imagination is the beautiful one. But you could also say that the one that reality forces you to make is a beautiful one. And I think that physics and mathematics is a bit like this. And in mathematics, you don't actually have any constraints. You can make beautiful things, and some of them might be realized in nature. But nature usually has its ugly parts and its constraints that force us to do things within our limitations. And I think that this is very beautiful. I think now I find most beautiful the things that are supposed to be traditionally ugly, such as, for example, solid state physics. When you have very incomplete description of what happens in your material, and you try to understand its properties. So you have some basic description of its atoms, but then you want to understand how it reacts to temperature or pressure, which is a very big jump. And it's ugly in the sense that there are too many gaps there. But I find it amazing that people can still make a path with a lot of gaps and a lot of black boxes. And that basically is the subject, I guess, of emergence and organization, and how come the world manages to make beautiful structures through this messy process. There are many things that we would deem beautiful that nature doesn't care about. And we have plenty of examples of such a thing. There's many beautiful theories that are wrong. So I do believe that what nature does, once we eventually understand, is beautiful. It's just I don't trust our sense of picking what is beautiful. And so I prefer to do it somehow in consultation with nature, even if it looks really ugly while you do it.
At first.
Hopefully at first. But the parts that will eventually become beautiful, I think, are now ugly. So I'm drawn to those ugly parts.
Nature ultimately is beautiful. But the beauty that we think we see may not be the beauty that really exists. Frank Wilczek considers the foundations of the world. A Nobel laureate in physics, he's the author of The Lightness of Being, which shows how the ultimate source of mass is pure energy. We meet in his home near MIT. How important, I wonder, is symmetry?
In 20th century physics, one of the great themes, I think maybe the greatest theme, is that the best guide to the formation of new laws is the principle of symmetry. Now, when physicists use the word symmetry, they mean something very specific. I happen to have this icosahedron handy. An icosahedron is a 20-sided solid. Each side is an equilateral triangle, and if you rotate it in very many different ways, it turns out to assume the same shape. And that's what we mean by symmetry, that there's a distinction without a difference. So, for example, the special theory of relativity is a postulate of symmetry. It's usually stated as that observers moving at a constant velocity with respect to one another see the same physical laws. Well, that's a symmetry. It means that those two ways of observing things are distinct, and yet there's no difference. And it's amazing but true that when we try to formulate new laws of physics, it's been a very successful guiding principle to suppose that the laws are symmetric, so that, for instance, you can have transformations of the laws of physics whereby one kind of particle transforms into another, and yet the equations overall remain the same. So they're distinct ways of writing the equations, but they don't make any difference in the end. And the fact that they don't is symmetry. And that says something very specific and profound about the equations. Not just any equations will be symmetric, just like not any old shape will be symmetric.
And when you find that, that's a hint, but not a proof necessarily, that your on the right track to something.
That's right. And we've gone one step beyond. Another powerful concept in physics has been broken symmetry. So, for instance, if I take this icosahedron and squish it a little, it's no longer symmetric. And yet, it's not arbitrary. It still has the same number of vertices and links that it had before. You might say, well, the number of vertices and the number of links suggest that really there was an icosahedron there and there's an underlying symmetry. And we see that kind of thing in the world. We see specifically, for instance, that the different interactions of nature, the strong electromagnetic and weak forces that go into our most profound description of nature, look similar and almost symmetric, but not quite. Now, if you let me take a very symmetrical system that includes them all and squash it a little bit, then it fits the world. So this has been a guide to trying to unify the different forces of nature. And it looks very promising, very right. A lot of what we do in fundamental physics is to try to guess symmetries and simple ways of breaking them.
The profound power of symmetry shows that while things may seem to be very different, in deep truth they can be very much the same. Symmetry is part of beauty. Is there more? I ask Freeman Dyson, a physicist and one of the world's most original thinkers. Always creative, Freeman sees new vistas of beauty. He's at the Institute for Advanced Study in Princeton, where we meet.
The history of physics, of course, has been one symmetry after another. We have been always amazed to find just how one can understand the laws of physics deeper and deeper by just looking at how things can be symmetrical in different ways. And the mathematicians very often have led the way by inventing symmetries before we discover them in nature. I don't try to explain beauty, and you can say some things contribute to beauty. First of all, to be simple in some sense, but not too simple. It has to have some sort of strangeness in the proportion, which is a favorite phrase of ours, and that's this characteristic of beauty. It's a little bit the same with human beings. I mean, it is a fact that we find people beautiful whose bodies are symmetrical, more or less, left and right, that the right ear is more or less the same shape as the left ear, and the right leg is the same length as the left leg. So we like people to be symmetrical, but not too symmetrical. If somebody is exactly symmetrical, then somehow it isn't so beautiful anymore. And I'm interested in exploring more than understanding, you might say, and when you're exploring, you're looking for irregularities, you're looking for new things that weren't seen before. So symmetry is not what you're looking for. When you try to explain things, then symmetry becomes important. And so science is part exploring and part explaining. I think the two are more or less equally important.
And need to be done recursively.
Yes, indeed. So you might say the frogs mostly are doing the exploring and the birds are doing the explaining.
And the birds and frogs are part of the same ecosystem.
Yes, that's a good metaphor.
Symmetries and broken symmetries construct the cosmos at all levels of reality. That's beautiful. Scientists often use beauty as their guidepost to seek the laws and regularities of nature, from quantum particles and forces of atoms to galactic structures and universe histories. Beauty in science is when complex things are explained by simple ideas. Ideas both concise and powerful, but not necessarily easy to understand. When the actions of a single force, gravity, can act over billions of years to form stars and planets and set the stage for the emergence of life, That's beautiful. And I am captured by it. Some say that discovering the beauty of the cosmos is the highest calling of human beings. Others, that it's a hint of the divine, the signature of the Creator, the supreme artist. The beauty of the cosmos is real. Interpreting it takes us closer to truth.
For complete interviews and for further information, please visit closertotruth.com.